Alright guys, welcome back. This is part 2 of our second example for the three-moment equation. Picking up right where we left off, we just found the expression where we have two equations and two unknowns for the internal moments at B and C. And just a quick recap was what we did is we had this beam up here. It's a 3-span beam with a couple different loadings on it. So first we drew the simply supported bending moment diagrams that would be supporting those given loads. From there we found out the areas of these and the distances of their centroids from the outsides when we're applying the three-moment equation. And then we applied the three-moment equation twice across span A, B, C, and then the second time was across B, C, D. And that basically led us to here where we found this expression where we have two unknowns, two equations and two unknowns. So I'm just going to solve this using a 2x2 augmented matrix. You can use substitution if you want. But basically we're going to find that MB is equal to negative 71.833 and MC is equal to negative 78.667. And we already knew from before that MA was going to be equal to 0 and also MD was going to be 0 because those are just at the ends of spans. Okay, so now what we want to do is we want to draw the actual free body diagram of each span with its applied loads and internal moments and internal shears, basically sectioned just right before the supports. So when I do this, I draw on the shears in the positive senses, and they're all unknown values, matching the positive sign convention for beam bending. And then we already know that MB and MC are negative, so what I've done is I've actually drawn these on in the negative sense and then made it a positive value. So basically this is a negative moment when we're looking at this free body diagram with a virtual cut here. This would be a negative moment, and then if we look at this free body diagram, where we have a moment, internal moment going, I guess, counterclockwise to the left of the virtual cut, then it also shows up as negative here. And then same thing here. The moment at MC was negative, so I've drawn them on in the negative sense. The moments on the ends are 0, so it doesn't really matter which way you draw those. All right. So what we want to do now is we just want to do the sum of moments about some point for each of these to basically find one of the shears, and then we'll do sum of forces in the y direction to find the other shears. So for the first section here, for span AB, we're going to find that VB1 is equal to negative 32.183 kilonewtons. So that negative sign indicates that it's actually going up, or we're actually experiencing a negative internal shear, right? Because it's opposite that positive sign convention. So then when we go to draw the shear force diagram, at this point, the shear force on the shear force diagram is actually going to be negative 32.183 kilonewtons. Now, because this is actually going up, then the force balance in the y direction is 50 going down, 32.183 going up, so VA has to be 17.817 kilonewtons. And because this is drawn in the positive sense, when we get a positive value for this, this means that the shear is actually positive. And again, so when we draw the shear force diagram in the next video, it's going to be starting at positive 17.815, basically just on the left-hand side of this span AB. All right, so we do the same thing for the second span. We take the sum of moments. Let's do the sum of moments about B. We're going to find that VC1 is equal to negative 15.683 kilonewtons. So this negative sign indicates that it's going opposite of the way we drew it. So for the force balance in the y direction, we have 50 going down, we have 15.683 going up. So VB2 is going to be equal to 34.317. And we're going to do this one more time for span CD. So we're going to take the sum of moments about C. We're going to find that VD is equal to negative 42.133 kilonewtons. So if that's going up, then we have 100 kilonewtons pressing down from the distributed load, right? 10 times 10, and it's passing through that centroid at 5 meters. So we have 100 going down, we have 42.133 going up. So the shear at C is going to be equal to positive 57.867 kilonewtons, just to the right of point C. All right, so now we know the internal shear and the internal moment at the very edge of each span. And that's enough information for us to be able to draw the shear force diagram, bending moment diagram, and then solve for the reactions. So I'm going to pause the video here and then join me in the third video, the final video for this problem, and we're going to go over just exactly that stuff.